Hey there guys, welcome to the next Chem Complete lecture for aldehydes and ketones. And today we are going to tackle forming ketones and how we can create that functionality. So if you didn't see the lecture that came before this one, it was on forming aldehydes. So I would encourage you to go watch that if you haven't yet. And then we will get started with this in just 1 second. So that's coming up right now. All right, before we get started, just a quick reminder, you can head on over to chemcomplete.com and we have lots of various resources over there. Some of the resources are free and available to you for no charge. And then we also have some very affordable guides that you can pick up, how to pass and prepare for organic chemistry. I have a very popular guide on spectroscopy, NMR, IR, solving unknowns, things like that. How to write proper lab reports for gas chromatography, big topics that students tend to struggle with. So do yourself a favor, head on over to chemcomplete.com at some point, and let's get started with our lecture. All right, now ketones. Ketones are going to have 4 major reactions that we've currently come across in an organic chemistry course by this point. Okay, now some of these are more exclusive than others, specifically when we talk about aromatic systems. So if you have had the aromatic reactions and that lecture, then you may be familiar with this particular example that's going to come up today. Okay, but what I want to start with is oxidation of secondary alcohols. So last time when we were talking about the aldehydes, we said that a primary alcohol can use a weak oxidizing agent, and PCC was the example we used. We also mentioned the Des-Martin reagent. That can be used to turn a primary alcohol into an aldehyde. Now, oxidation of secondary alcohols are going to yield ketones. So, if I take a very basic secondary alcohol, and I subject it to any type of oxidation, I should successfully get a ketone in return. Now, when I say any type of oxidation, what that means is you can use a weaker agent on a secondary alcohol, and you will still get your ketone. So, the weaker reagents are good at oxidizing secondary alcohols. Their primary focus is that they can stop the primary alcohol oxidation from going to a carboxylic acid. But they are still viable here. So PCC would be an option. Okay, but I'm just going to use a different one for the sake of variety because we want to have as much exposure as possible. And I'm going to say that we'll use CrO3, which is another common oxidizing agent. However, CrO3 is a strong oxidizing agent. So if I were to use this on a primary alcohol, I would indeed get a carboxylic acid. I would not expect the aldehyde. Now, if I continue forward, this oxidation process is going to lead to the ketone that I would be looking for. Okay, so again, important lesson with counting the carbons, okay, is that the number of carbons here, 1, 2, 3, should always be the number of carbons over here, 1, 2, 3. Okay? The only time that might be changing is if you have a reaction where you have the addition of carbons. So for instance, a Grignard reaction would add additional carbons, okay? And we are going to take a look at a reaction here at the end of this lecture that does just that. It has the ability to add additional carbons, and that'll be one way that we can create ketones. So we'll look at that in a few minutes. Okay, now, number 2, this is what I was talking about a minute ago, the Freidel-Crafts acylation reaction. Okay, the alkylation would just add regular R groups to an aromatic ring. The acylation is going to add a carbonyl with an R group, and then the other R group for your ketone would be the aromatic ring itself. Okay, so you can see it says aromatic exclusive in the parentheses here, and that's because Freidel-Crafts acylation is great for making ketones on aromatic systems, but it doesn't have the same sort of broad application that, for instance, the oxidation of a secondary alcohol would have, because it has to be seated exclusively in an aromatic system for this reaction to work. Okay, so either if you're being exposed to this for the first time, or most likely if this is a reminder for you, you've got an aromatic system. We're just going to go ahead and give classic benzene here. And when this system is given the following reagents: an acyl chloride, which is going to be a chlorine group on the other side of your carbonyl. Okay, so let's do a simple example. I've got CH3, C double bond O, and then I've got a Cl. Okay, so this is another reagent we're going to come to in just a minute. The acyl chloride is very important in making ketones. Okay, the catalyst for this is an aluminum-based catalyst. It's AlCl3. This AlCl3 will couple with the chlorine from the acyl chloride and create a cation type of formation on the carbonyl, and then the aromatic system can attack that. Hydrogen can be removed, and you return aromaticity at the end of that reaction because it is favorable from an energy and a thermodynamic standpoint. Okay, and so what we end up with is an aromatic ring that then has an attachment to the carbonyl and whatever R group you had. So in this case we had CH3, right? We made ourselves acetophenone here. And if we look at this, this is a way that we can create ketones that is exclusive, again, to aromatic systems. All right. The oxidative cleavage of various alkenes. Again, if you did not take a look at the previous lecture, I would encourage you to, because this reaction can make aldehydes and ketones. And I'm going to go over very quickly the same sort of scenario. So let's say that I have an alkene. Okay. And the alkene's got some sort of a formation like this. Okay. I can expose this alkene to, number one, ozone. So this is often called the ozonolysis reaction, also known as an oxidative cleavage. And then number two, you're going to have zinc metal along with some source of acid. Now when you have this, it's going to cleave this double bond right here, and the easiest way to form these products is to just redraw it with the double bond, but instead of attaching it to the other carbon, just place an O in it. So the left hand side would give us an aldehyde. We would end up with this, right? And the right hand side would give us a ketone. So this is a valid reaction for producing ketones. There's obviously a very large variety of alkenes out there, and so you can get all sorts of different compounds when you're doing this. Depending on the structure of the alkene itself, you may get 2 ketones, you may get 2 aldehydes and no ketones, right? So if this were to be an H instead of a CH3, then you would be talking about this having 2 different aldehydes as the products, but no ketones. Okay? So oxidative cleavage of alkenes is a viable way to create ketones. Now this one's relatively new to most students by the time they get here, depending on their studies. So the Gilman reagent is kind of similar to the Grignard reagent, but there are some big differences. Okay? The biggest difference is that the Gilman reagent, generally speaking, is a weaker reagent than the Grignard reagent is. And that is important because we're going to use the Gilman reagent to create a ketone. But if you remember, Grignard reagents react with ketones. So I can also use a Grignard reagent to make a ketone, but then additional Grignard material will react with that ketone and kind of destroy it or take it to the next synthetic level. A Gilman reagent will not do that. You can stop at the ketone stage with a Gilman reagent. Okay, so what you need is, to start, you need an acyl chloride. So again, we're going to keep our examples simple as we're exposing this material for the first time here. Okay, this is an acyl chloride. Acyl chlorides are going to be R, C double bond O, Cl. Sometimes you'll hear them called acid chlorides as well. okay, referring to a Lewis acid because they very readily accept electrons from any type of incoming nucleophile. But this is one of the carboxylic acid derivatives that usually gets studied after the aldehyde and ketone chapter. So we'll be revisiting this when we do aldehydes, when we do carboxylic acid derivatives on here. Okay, so you have your acyl chloride. Then you need the Gilman reagent. Now the Gilman reagent is going to have 2 of whatever R group you want to add. So again, for the sake of keeping things simple, let's just add a CH3. So what we do is in parentheses, we put the CH3 and then we say we need 2 of them. That is going to be coupled with a copper, okay, and then you're going to have lithium that is kind of putting this together as a salt. So this is a negative complex and this is a positive complex here. They come together and you get your Gilman reagent. Okay, now the Gilman reagent is going to generate the CH3 group that you need, kind of like a Grignard reagent would. Okay, so this will come in, you're going to attack the carbonyl. This will then open up as it would in a normal nucleophile attack. So again, very similar to the first step of a Grignard, but here's the big difference. We don't, at this step, need to protonate this oxygen. So in the Grignard, you would need to turn this into an alcohol at this point with some sort of acid. But we have a chlorine, and what we know about halides is that they make excellent leaving groups, and that's exactly what's going to happen. This will leave very readily, and instead of protonating this, the set of electrons will come back down to reform a pi bond. And so if the chlorine has left and is no longer there, well then I've got the 2 methyl groups and I've got the carbonyl back. So methyl group, carbonyl, methyl group. This is a ketone, right? So the use of the Gilman reagent can be utilized in the formation of ketones, provided you have a proper acyl chloride for the ketone that you would like, and then you use your Gilman reagent along with that. All right, so that is going to finish our lecture on the formation of ketones. So the next thing that we are going to cover on the channel is that we are going to take a look at some reactions of these individual aldehydes and ketones. And we're going to start with the cyanohydrin addition, and we'll move forward from there to some of the other very common, well-known reactions. Many of these reactions are going to be important when you go on to, or if you go on to, look at biochemistry or take a biochemistry course. Okay, so that does it. Please remember to like the video if it helped you. You can subscribe if you want to stay up to date with all our content and support the channel. And if you leave a comment because something may be confusing you or you just want to drop your thanks, I am more than happy to interact with my community. And other than that, again, shout out to chemcomplete.com. Go over there and check out what we've got available. I think it could really help you. And I will see you guys for the next lecture, cyanohydrins.